Now we're going to have to also do that same thing. We're going to have to go from 0.01 to L over 2, right? Because again, we're going to run into trouble when we put the 0. So we put here 0.01 to L over 2, the total length of the half the length of the rod, and then the integral of that is what? Negative 1 over x from 0.01 to L over 2, and then we get what? What is that? 1 over 0.01, which is 100, right? 100 minus 2 over L. I kind of did that quickly. I put this in, and I get a negative. Then I put this in, I get a positive, right? And then 1 over 0.01 is 100. So now, based on this, this one is kappa. So kappa is equal to Q divided by 2 times 100 minus 2 over L. This is just so that we can get rid of the kappa. And then take the kappa, put it over there, and now you get an actual answer for the force. Okay? So F is equal to 2K Q2 over R cubed. Kappa is equal to Q1 divided by 2 times 100 divided by 2 over L. And then you got the 4.8633, which was the integral. And this 2 cancels with that 2. Okay? Now I can put in the numbers here and see if my final answer makes sense. So what are we going to do now? We're going to use the length of the rod is 12 meters, right? So we use 12 meters, and the radius is 12 over pi. 12 over pi, and this whole thing is 12 meters. So 9 times 10 to the 9th. This is again 1 microcoulomb, 1 microcoulomb, so 10 to the minus 12 microcoulombs. 4.8633 divided by radius cubed, so 12 divided by pi cubed times 100 minus 2 over L is 12. So put that all in, put it in your calculator, and see what we get here. Our assumption, our prediction was that it's going to be greater than the semicircle uniform rod. It's good? Our prediction is not good? No? What is it? 7.87 times 10 to the negative 6. Oh, that's way too small. 7 point. Oh, it's too small, huh? But we predicted that 7.86 times 10 to the negative 6. Newtons. No, somewhere we went wrong here. Let's see. 2K, no, it can't be smaller because there is more cancellation here where there's less charge, so it should be small. It should be larger. Our logic was right. 2K Q2 over R squared. You got lambda dx sine theta dx lambda is kappa x to the minus 2 kappa dx is r d theta, and x is r theta. Let's see here. Oh, you know what? Maybe this might have something to do with it, because if this, the way that the x is measured is what? From the center to the element, right? The theta, which I'm taking the sine of, is this theta, right? This theta is equal to this theta. So if I'm going to say x is r theta over here, see over here I said x is r theta, right? It's really not r theta, because this, if I define this as theta, and then I can say this is theta, then I can say x is r theta, right? Then I could put x is r theta here, r squared theta is squared. Then I could put dx is r d theta. Then I'm going to have to put cosine theta here. It's the cosine that survives, not the sine. Okay? Now, that didn't make a difference for the uniform. Why? Because for the uniform, I didn't have, the density wasn't changing as a function of the position. So it didn't matter if I defined x from the end or this end or from the center, because it was a uniform rod. But if the rod is non-uniform, then the definition of the x matters. So I have to put here x, I have to put theta there, I have to put theta here. This is awesome, awesome. We're learning a lot of geometry here. So I'm going to have to do here cosine theta if I want to use x is r theta. Now, I don't know if this is going to help us out here, but I'm hoping here. Let's see here what happens. Cosine theta, then I could put x is r theta, so I put cosine theta, and I go from 0 to pi over 2. So I'm going to have to integrate that again. Let's see now what I get. Is that a big difference in the integral? Probably so, right?